Okay, so number 2. So I'm just going to go through the steps like we always do. So I'm going to first calculate the external loads, then I'm going to calculate the internal loads, and then I'm going to go to the stresses. So for the external loads, I'm going to do a free body diagram of the whole thing. And 1, 2, 3. So this is here. We have a force vector here from the pin of, I'll call that RA. We have an upward force here, RB. None of the vertical stuff is going to, all the vertical stuff is going to be 0 just because of the nature of the external loads. There's no weight or anything. Okay, and Newton's second law says negative 6,000 minus 8,000. Well, why don't I'm just going to do it as vectors. So negative 6,000, 0, plus negative 8,000, 0, plus RAX, RAY, this is 10,000, plus 0 RB, plus 10,000, 0 is equal to zeros. And so the X equation says RAX is equal to 4,000. And RAY is equal to 0. I guess we don't know that yet. We'd have to do that with so we'll use the moment equation. I'll put my about point here. And so the only moment is, so plus or minus 1, moment arm of 1 times RB. That would be around that red dot. That would be counterclockwise, so we want positive. That's equal to 0. So RB is equal to 0. So RAY is equal to 0. And that makes sense. I mean, there's no external vertical stuff going on. You wouldn't expect there to be any vertical reactions. And now we'll go to our cuts. How many cuts do I have to make? 3. There's 2 places where there are point loads or changes in distributed load. So we're adding 2 cuts to the default of 1. So our first cut is going to be for X values between 0 and 1. And we have the 6,000 here. And then we have our internal loads. So Newton's second law says negative 6,000 plus T is equal to 0. So T is equal to 6,000. And then if you did the y Newton second law equation and you did the moment equation about the z-axis, you'd get that v and m are both equal to 0. Because there's nothing, those don't have anything to counteract for equilibrium. Then we'll go to cut 2. This is for x values between 0 and 2, or x values between 1 and 2, sorry. And we're going to go all the way from the left to some point after the 8,000 Newton. So we have a 6,000 here. We have an 8,000. Newton's second law says negative 6,000 minus 8,000 plus t is equal to 0. So t is equal to positive 14,000. If we did the y Newton's second law equation and the moment equation, again, we'd get that v and m are both equal to 0. And then cut 3 is for x's between 2 and 3. So this time we have 6,000, 8,000, and our RAX is 4,000 going the other way. And then we have our internal loads. Newton's second law, negative 6,000 minus 8,000 plus 4,000 plus t is equal to 0. So t is equal to 10,000. And v and the bending moment are 0 again. So those are 3 internal tension compression values. You can see they're all positive, so it's tension at every point, but the value jumps at the external loads. And so now we'll do it for cut 1. Calculate the stress. We don't have to deal with the stress due to bending moment or shear force. For the one due to tension, we know that this is equal to the internal tension divided by the cross-sectional area, and it gives us the dimensions. So 0.05 by 0.02. So that is 0.001, right? So 10,000 divided by 0.001. Oh, I'm looking at the wrong one. Yeah, cut 1, it would be 6,000, right? Yeah. I was looking at the whole thing. And so this is 6.0 times 10 to the 6 pascals. And For different points along the beam, calculate the stress tensor. And then we're going to calculate the strains for two different materials. So the stress tensor, the only thing going on is internal tension, so we don't have to add any other stress tensors to it. This is 6 times 10 to the 6, and zeros. If you wanted to get the maximum shear stress, you could. So it says now, assume that it's aluminum. So E and Poisson's ratio for aluminum. You can just Google that or whatever. So we'll call, for aluminum, we'll call this 70 gigapascals. So 70 times 10 to the 9 pascals. And the Poisson's ratio we'll call 0.33. And then the Voigt strain is the compliance matrix with these values times the Voigt stress, which is 6 times 10 to the 6, and zeros all the rest of the way. We only had stress in that one direction. Why is it that we have strain in 3 directions? What's the name of that phenomenon? Or mathematically, what causes it?
We're multiplying with the compliance matrix.
So yeah, you get it from multiplying by the compliance matrix, and it's called the Poisson's effect. It's the fact that when you, like when in a cartoon, when they whack a cat on the head, he expands this way. That's the Poisson's effect. If you press down on something in the other dimensions, it expands. And if you stretch it on the other dimensions, it contracts. Okay? So even though there's only stress in one direction, you get normal strains in along all 3 axes. Okay? What do you think is going to happen when we put in the values for steel? So we're going to keep this same stress tensor, but our compliance matrix is going to have the values for steel, which has a bigger E value, pretty similar Poisson's ratio. Do you think the strains are going to go up or down? They're going to go down because the stronger a material is, the less deformation you get for the same load. Okay, so now we'll do it for steel. For all of these, there's always a small range of possible values depending on the alloy that's used and stuff. But I'm going to use 200 times 10 to the 9 pascals, and I'm going to use a Poisson's ratio of 0.3. And so my Voigt strain is the new compliance matrix times that same stress, because nothing about the state of stress would change based on the material. And this time we get values of positive 3 times 10 to the minus 5, negative 9 times 10 to the minus 6, negative 9 times 10 to the minus 6, and then 0 for the shear strains. So just like you would expect, under the same amount of loading, you get a bigger deformation for the weaker material, aluminum, and less deformation, for the stronger material, steel, stiffer material. Okay, and then the problem asks you to do that for all the different cuts. What about, so I'm treating this as representing the strain in the material, the stress and strain in the material everywhere along that cut. So for every X value inside that cut, but that makes sense because the internal tension compression is the same for everywhere inside that cut. But I'm also using this to represent every point along the cross section inside that cut. Does that make sense here? That I would have the same stress and strain for every point along the cross section?
Yeah, because there's no bending moment.
Exactly. So bending moment and like the stress due to bending moment, the stress due to shear force, and what we're going to get into next, the stress due to torque, they all depend on where on the cross section you are. But for tension compression, there's no dependence on where you are in the cross section. Okay? All right, I'm going to stop that one there. Let's look at number 4.
So for the others, the only thing that changes is the tension, right?
That's right. So you just plug in so like for cut 2, you just plug in 14,000 for T. You get a new value here, new thing here, and yeah, but everything else is the same. Okay, so number 4. Well, if you haven't done that one yet, don't do it.
Is there no bending moment? Because I was confused. Like
There is a bending moment, and not only that, I don't know how this. I feel like I might have used old questions here. There's a few problems with this. So let me enumerate all the problems with this. The first one is that this couple here would, if this really was just a roller like this couple would just make it flop over the top. So it wouldn't be static.
Yeah, that's what I'm trying to figure out.
Okay, so that doesn't make any sense. That's the first thing that doesn't make any sense. The second thing is I put this couple in here just so that all there would be is a tension compression value and a bending moment. But that's not how this works. So say that this was a pin and slot joint, or say that this couple went the other direction. That's going to create a reaction force here. And that reaction force is going to create a shear force. So this really isn't a problem that I think when I made it, I assume when I made it, I was thinking that this would only have tension and bending moment, but that's just not how it works. Okay. So I don't know.
I can tell what you're like trying to do, but now it's like, oh,
Yeah.
I'm not doing it.
That's sort of how I feel looking at it. Like, yeah, I can tell what I was trying to do. It makes me think there's probably a newer set of problems, and I accidentally put the old ones up there. Okay, everyone's good on number 5, or I haven't assigned that yet. Okay. And now number 4 on stresses in beams.
For the introduction, it's not solvable or current methods or it's
Let's say it's not solvable. Well, I guess now that we've talked about stresses due to shear force, you could deal with the fact that, well, let's do it. And let's just make the correction that makes it solvable. It's not doing what I intended it to do, but it's still doing something, and now we know how to deal with it anyways, so let's just do it. What do we have? Somewhere better to be? Is it? That's good. Okay, so what I'm going to do to make this solvable, to make it static, is I am going to treat that roller like it's a pin and slot joint. Okay, so imagine that, so imagine that if you try to make this flop over, if you apply a couple to make it go this way, this will still hold on to it. Okay. So that's what would happen if this was a pin and slot joint and the slot was horizontal. Okay. So I'll draw what my reimagined problem is like, so you have a pin joint over here, and I guess there's a couple ways I could draw it. So say that there's a pin there that goes in a slot. Okay. And then we have this stuff. 2000. This is such a huge couple. Holy moly. Did I say this before this semester? Anybody have a guess at what kind of Newton meter couple you can apply with a screwdriver? Yep.
I also noticed that there's no way. This 2 meters.
2 meter. Yay. I did one thing right. Yeah, what kind of couple can you apply with a screwdriver?
I remember 50.
How much?
50.
That would be really, really high. But I mean, it's kind of in the right ballpark. I'd say 10 is probably more reasonable, you know? So this is 200 people turning screwdrivers as hard as they can.
How about impact drill? How much?
I don't know. I don't know that.
What kind of cause that copper like these or like those?
What could produce that? I mean, really, any kind of motor or engine could, you know, industrial things could produce that. But that's really big. Okay, so what do we have to calculate? First, we have to calculate the reactions. So free body diagram of the whole thing. We have an RA over here and a 4,000 here and an RB. The only thing that's different this time than the way it would be if it was a roller is now this RB can be negative and that joint can still sustain a negative value of RB. With a roller like this, it would have to be upwards positive the way I did it. And then we have the 2,000 here. So Newton's second law says RAX, RAY plus negative 4,000, 0, plus 0 RB is equal to zeros. So we know that RAX is equal to 4,000. And we know that RAY is equal to negative RB. And then I'll go to the moment equation. And I will put my about point here. The 4,000 doesn't produce any moment. The 2,000 does. That's counterclockwise, so it's positive. And then the RB does. That's plus or minus a moment arm of 2. times the force. That would cause a rotation that was counterclockwise, so we want the positive. So RB is equal to negative 2,000. And that's where the problem would have come in with the roller, that a roller can't produce a downward.
Would you be 1,000?
What?
Would you be 1,000?
Yes. I'm using the new math.
Oh, okay.
And then, so then RA is 4,000, positive 1,000. And now we have to do our cuts. So cut 1 is for x's between 0 and 1. So we have 4,000, a 1,000. We haven't gotten to that middle part yet. We haven't gotten to these two things yet. And so all we have is T, V, and M. And so Newton's second law says 4,000, 1,000 plus T negative V is equal to 0. And so T is negative 4,000 and V is positive 1,000. And now the moment equation about the z-axis, I'll do my about point here. So all we have is m minus vx is equal to 0. So m is equal to 1,000x. These are valid on that first half.
Instead of the percent, what we sometimes put s and sometimes just put the distance, the number.
Oh, yes. Yes, good question. So often on problems like this, since you can only calculate stress at a single point, right? Stress represents a single point. So often on problems like this, I'll tell you what point I want to analyze. I'll say I want to be 3/4 of a meter from the left end or something, and I want to be at this point in the cross section. Okay. In this problem, I didn't do that though. I said we want to, over all of the points in this whole beam, we want to figure out where we have the greatest absolute value of normal stress. Okay. And so in this problem, we have to consider all the possibilities. So I'm going to calculate. So what I'm going to do is I'm going to find locations where my internal loads have big absolute values. And then I'm going to analyze those x values. Okay, so it just comes down to whether I give you a specific point to analyze. In that case, you don't have to do the internal loads generally. You can just go right to that point and do the cut. But in this case, I have to be more general to try to get a sense of what's going on. Okay. Like, for example, I mean, we can already tell some stuff like, so where on this first cut, where would we be most concerned? What x value would we be most concerned about here? Well, T and V don't change along the cut, but that m value goes from a value of 0 when x is 0 to 1,000 when x is 1. So I know in this cut, I'm most concerned as we get close to x equals 1. Okay, but I wouldn't have known that without calculating the general internal loads. And now I'm going to do the same with cut 2, and we're just going to sort of see what we have and see if we can figure out where these values are going to be big. Okay, so cut 2. This is for x values between 1 and 2. And this time we have the 4,000 and the 1,000. And we also have the 4,000 going this way. And we also have the internal loads. And so Newton's second law says 4,000, 1,000 plus negative 4,000, 0 plus t negative v is equal to zeros. So t is equal to 0. V is equal to positive 1,000. And then the moment equation about the z-axis, my about point is at the left. And let's see what we got. No moments produced by either of the things at the about point. No moment produced by this horizontal force. So again, we just have m minus vx is equal to 0. So m is equal to 1,000x. And these are valid on the interval from 1 to 2. Yeah. Okay. So now we have our internal loads, and we have to think a little bit about what's going to happen when we calculate stresses from these. So from the bending moment, we're always going to have one positive normal stress and one negative normal stress, at either the top or the bottom. Okay. So the biggest absolute value of normal stress is always going to be it's always going to be when the direction of the normal stress due to tension is the same as the direction of the normal stress due to bending. Okay, so we're going to have to consider whether we're most concerned about points on the top or points on the bottom. Okay, so let's think about what's going on here. In both of these two cases, all right, so what are some of the things that could happen here? We could have our biggest stresses on cut 1 at the top of the beam. Since this is so think about the way this is bending. Like this. Okay. Okay. So since we have positive bending moments the whole way, it's curving like this. So is the bending moment going to produce a positive or a negative x normal stress at the top of the beam? Is it going to be tension or compression at the top? Compression, and then tension at the bottom. So then we have to ask ourselves, okay, on cut 1, is this in tension or compression? Due to tension compression, is the stress going to be positive or negative? Because we're most concerned about when those are working together to break this thing. If they're fighting against, if one's trying to break the thing and one's playing defense on it, that's not going to be as much of a problem as when they're working together. You know what I mean? So we're most concerned about the top of the beam when both of these are putting it in compression. Okay, so on cut 1, at the top of the beam, the internal tension and the bending moment are both causing compression. So on cut 1, we know for one thing that we're most concerned at the top. And then what about the...
Why compression shouldn't be like negative? It would be...
Yeah, so remember that the stress due to bending moment is this.
Oh.
And so if you have a positive Y value, you have a negative normal stress. Okay. And then we have to think about where on cut 1 we're most concerned about this. Well, there's it doesn't make any difference to us what X value we're talking about with tension or shear force. Those are constant along the cut. But the bending moment is going to get bigger as you go, as X gets bigger. So we're most concerned at the top about this breaking. And we're also most concerned at X equals 1.
Wait, how do you know we're most concerned about the top versus the bottom?
Because we're most concerned about fracture or damage when the stress due to bending moment and the stress due to tension compression are in the same direction.
Oh, I see.
Okay, so that's how...
Tension's going in and the bending moment causing it to go in.
Yeah, so the bending moment is making it compress on the top, which is what the tension is doing on this cut, because it's negative 4,000 for internal tension. So at the top, these two things are working together to cause compression. At the bottom, they're fighting each other. One is causing compression. The other one is undoing that compression with tension. So okay. All I can say based on this is if the worst stress happens on cut 1, it's going to happen at the top of the beam and at X equals 1, or as you approach X equals 1. So now we have a place where we want to do these calculations. Let's calculate that stress. Okay. So, our total stress is going to be our stress due to tension plus our stress due to bending moment plus our stress due to shear force plus our stress due to torque, but there's no torque. So all we have to worry about is those. Okay, so I'm going to start with the stress due to internal tension. So XX is equal to the tension compression value divided by, this is rectangular, 0.05, 0.02, so that's 0.001 is the cross-sectional area. And so the value here is 4.0 times 10 to the 6, negative. And so the stress tensor is negative 4.0 times 10 to the 6, zeros everywhere else. And now we'll do the calculation for bending moment. Okay. This is a rectangular cross section. So I is equal to 1/12 times the base times the height cubed. And that is 2.08. And then 3 is repeating, times 10 to the minus 7 meters to the fourth. And our y value at the top, so this is, we're doing this at x equals 1 and at the top. Well, this thing has a height of 0.05. So what's the distance from the neutral axis to the top?
Oh,
0.025. And then is it positive or negative if we're going to the top? Positive, yep. So y is equal to positive 0.025 meters. And then the bending moment is 1,000 times x. We want it at 1, so this is just 1,000 Newton meters. Okay. And now we can use the formula that says the XX normal stress is equal to negative M Y over I. And so that is negative 1.2 times 10 to the 8. That's huge. By the way, I don't think the material is going to survive this, but that's the value we got. You know, that's the kind of reason why you do calculations like this. And so the stress tensor due to bending moment is, so I'll write that as negative 120 times 10 to the 6, and then zeros everywhere else. And this is pascals. And then we have to do the shear stress. Well, we already assumed that this value is going to be at the top. I think I might have been a little quick to make that assumption because we should see what we should see how the shear stress compares to the bending moment, you know, because remember, what's the shear stress going to be at the top and bottom of the beam? Do you remember? 0, yep. So remember, bending moment is 0 at the neutral axis and gets bigger in absolute value as you go towards the top and the bottom. The stress due to shear force is maximum at the neutral axis and goes to 0 as you go to the top and bottom. So if it turned out that that stress due to shear force was really big, way bigger than the bending moment, it might not be the case that our maximum value in total is all the way at the top, you know. So this is the kind of, I don't know, you just have to sort of think your way through this stuff. I don't really have a system for you, you know. But let's see what the maximum stress is due to shear force and just see if there's any. So right now we know that at the top, the XX normal stress is equal to, we had -4 for one, minus 120 for the other. So this is minus 124 times 10 to the 6 pascals. And now let's think about the stress due to shear force. So is this ever big enough to make up for the bending moment? It's at a max at the neutral axis, max absolute value. So let's see what it's doing at its maximum absolute value. So this formula is tau xy is equal to negative VQ over IB. And at the neutral axis, so this is 0.05. This is 0.02. This is our area A above our desired line. The centroid is right in the middle. And so this distance is going to be, from the neutral axis to the top would be 0.025. The distance to the centroid is half of that, so 0.0125. The shaded area is 0.025 times 0.02. So that's 0.0005. And so Q is equal to 0.0005 times 0.0125. So that is 6.25 times 10 to the minus 6 meters cubed. And so tau xy is equal to, what's our shear force on cut 1? Positive 1,000. That's the same over the whole beam. So we have negative 1,000 times 6.25 times 10 to the minus 6. Our I that we calculated before was 2.083 times 10 to the minus 7. And our base is 0.02. And so the biggest absolute value of shear stress we could get is negative 1.5 times 10 to the 6. Okay, so what did we learn there? So the stress due to bending moment is a different order of magnitude than the stress due to shear force. So I'm gonna stay concerned with the top. I'm not gonna worry about the effect of the shear force. Okay, so for cut 1, we get that the total stress tensor is negative 124 times 10 to the 6, 0, 0, 0, 0, 0. Okay, like that. Now that we've figured that out, we can go to cut 2. And remember that cut 2 doesn't have any internal tension. So we're only worried about the bending moment at the top on cut 2. So our total stress tensor is the stress tensor due to tension compression plus bending moment plus shear force plus torque. But the only one that's, I'll leave that shear force one in. But this time we have 2 of them that are 0. Are you with me on that? Or is anyone with me at all anymore?
Why do we not add this shear force onto the total?
Because I'm still only looking at the top of the beam, and it would be 0 at the top. So I'm still, well, this time it doesn't matter if we look at the top or the bottom. They're going to be, in absolute value, they're going to be the same stress due to bending moment. I'm going to look at the top again, but I could just as easily look at the bottom and we get the same answers. So the stress due to bending moment, our formula is this. I doesn't change. That's just a function of the cross section. Y doesn't change. But M does change. So our Y is still going to be 0.025. Our I is still going to be 2.083 repeating times 10 to the minus 7 meters to the 4th. But this time our bending moment is going to be for cut 2, this time it's going to be 2,000. So sigma xx is negative 2,000 times 0.025 divided by 2.083 repeating times 10 to the minus 7.
What did you get? I?
We already calculated that before. Where was it? Here. 1/12 times the base times the height cubed.
Oh.
And we get 240 times 10 to the 6. This is negative pascals. So our total stress tensor is negative 240 And so where is the bigger one? From cut 1, the biggest value we could get was negative 124. Now the biggest value is negative 240. So at the right endpoint, what we've figured out is where this has the biggest value of normal stress. And I don't think there's any material that can survive that. I'm not really a materials science person, but I think it's correct that that'll break anything. Any other questions about that one? That has a lot of just like thinking your way through it. Yes.
Grab the shear.
Well, since I'm doing it at the top of the beam, the shear contribution is 0. If we did it a little bit, if we did it a little bit away from the top or the bottom, you would have a shear contribution that you would have to calculate.
I have a question if the shear calculation.
Yeah.
What is a Q?
Q is, so the best I can do with, so the meaning of Q, which I think would probably be called the first area of the shape above a line or something. Like it would have some mathematical name like that. But I just call it Q. So what's the meaning of Q? So if you have a shape, and it doesn't matter what the shape is, okay, this shape has a centroid, and the neutral axis goes through the centroid. Okay. And then you have a line of interest where you want to calculate the Q value. Okay.
Do we define the line of interest for like problems given on a test, or are you gonna be like find?
Usually I just tell you what it is. On a test, I don't think I could really make you go through a thought process like this. But in a problem like this, you have to think about what that line of interest is. But okay, so now above the line of interest, there's this area. Okay, area A. And that area A has a centroid somewhere. Okay. And then there's a distance from the neutral axis to the centroid of that area, and I'm going to call that D. And Q is equal to that area times that distance D. And remember that D is an absolute value. So even if you're going down below the neutral axis, it's still positive. So I think that picture is probably more helpful than trying to describe it in words, but Any other questions?
How did you find it so quickly?
Because it was a rectangle.
Okay,
So that just makes it really, like, imagine trying to do it for this shape. It'd be chaos. But, well, the good news is we can only use our shear force, our stress due to shear force formula for rectangular cross sections where the height is bigger than the width, or for along the neutral axis for circular cross sections. Our formula doesn't work for anything else. So even though you could calculate Q for any cross-sectional shape, there's only two that we ever have to do. And they're two easy ones. So for rectangular cross-section, I was doing, my line of interest was the neutral axis. Okay, because I know that's where the stress due to shear force is going to be biggest. So so the area is 1/2 of the area of the whole thing. That's A. That's easy to calculate. And the centroid is just, it's half of the way from the neutral axis to the top, which is easy to calculate, and then multiply those two together. So yeah, for a rectangle, it's really easy.
and for a circle, what?
Well, okay, so for a circle, you only ever need Q for the neutral axis. Okay, that's not true with a rectangular cross section, but with a circle, that's the only time we can use it in any formula anyways. So let's do this calculation. I mean, really, for Q, it's just always going to be the same formula. So there's the neutral axis, and that's also our line of interest. And so our area is half of the area of the circle. And the centroid is, here's our D. This is our A. So A is pi r squared over 2. What was the formula for the centroid of a quarter circle and a semicircle from last semester? That is the area for a quarter circle. So let's see. For centroid, I got it all here somewhere. Okay, so where were we doing centroids? Yay, found it. So for a quarter circle, 4r over 3 pi. Okay, so, oops, I called this y. I should have called it d. So 4r over 3 pi. Okay? So Q is equal to pi r squared over 2 times 4r over 3 pi. The pi's cancel. That 2 makes this a 2. And so we get 2/3 r cubed. And since that's the only line of interest that we can ever use, it never changes from this.
I was wondering where that came from.
Oh, okay.
At the answer sheet, there's like a time where
Oh.
was 2/3 R.
Uh-huh.
Where did this come from?
You could even go farther than that because I is always the same for a so for a circular cross section, I is equal to, I don't remember that formula. Let's see, where would that have been?
Is pi r to the 4th over 4.
Okay. Okay, yes. So this is pi r to the 4th over 4. Okay. So your XY shear stress is negative shear force times this Q. So I'm going to write that as 2/3 R cubed. And our B is always going to be the same because we're always doing it right at the center. So that's just going to be 2R. And so now we're going to divide by I. So divide by pi r to the 4th over 4. And now divide by B. And a bunch of this stuff cancels. These cancel with those. This makes that a 2. And you get a formula negative 4 over 3 pi r squared times the shear force. I think that's right. I don't know. But so basically, like, since you're always doing the calculation with a circular cross section involving shear force at the neutral axis, it's always the same formula for the stress due to shear force, just depending on the radius and the shear force. Any questions about that? Okay. Well, let's stop there. And on Monday, we'll get into stresses due to torques. Yes.